Hi, everybody. Welcome back to Goju Tech Talk. The dog has just left the building. That's kind of sad. Anyway, tonight we're going to talk a little bit about what I think is potentially the future of software. And I don't know that I'm entirely right about this. I want to start by saying there's still some fuzziness in my head. But in general, I think directionally, this is where we're going. And I'll talk a little bit about the old way that or the way maybe we do software today, but that's changing. Then the three pillars of machine programming, just to give some background on MP if you're not familiar with it. Then we'll talk a little bit about the bifurcated space of MP, and then we'll get into how I think this relates to the future of software development. Now, one of the things that I try really hard to do is sort of straddle this line between being a researcher and being an engineer. And I think that, at least for me, this is important because when you're maybe just on the engineering side, it may not be clear to you how research advances are going to impact you and your engineering discipline. And without that information, it's hard to sort of navigate this space in a way that is super meaningful. Not impossible, but I think more challenging. Or at least it was more challenging for me when I was just an engineer. On the other hand, while research, I think, can give us interesting ideas, what I've often found is the researchers that I've worked with that don't have a strong background in engineering for the discipline that they're working in often have trouble contextualizing the value of the research that they're building because they can't quite see exactly how these things would be applied practically. And so you can kind of see that if you're just in the engineering space, you might be really good at building stuff, but have a hard time seeing what the future is. If you're just on the research side, you might have an idea on how to explore ideas, but not understand necessarily which ones are the most relevant and useful for actual application. And so part of my path in life has been to try to navigate the space where I'm doing both. I'm doing research, but I'm also doing engineering, and I'm trying to marry the two so we have essentially applied research. That's the part that I think, at least for me personally, is the most interesting because I get to take the research ideas and then build real systems, not just research toys. No disrespect to the research community. I love research. It's super awesome, but let's just be honest for a second. A lot of the early research systems are mostly toys, and that's okay, right? That's actually not a knock. That's just me being honest in that they're not meant for prime time. They're more just a demonstration of a prototype. You're demonstrating the validity of some idea. So I wanted to start with this because what I'm going to talk about is based on my experience in both of those areas, which I think gives me perhaps a little bit more of a nuanced understanding of how to reason about these things, how to describe them and sort of see the future unfolding. All of that said, I don't think I have this totally nailed down. And as we get into some of the slides, we're going to go over some of the slides that I actually teach at the university. I'll tell you the parts that I'm a little blurry on, so you know what parts I think I'm fairly certain we're moving toward, and other parts where it's like, I don't know exactly how this is going to pan out, but I have some sneaking suspicion. Now, all of that said, a lot of what we're going to talk about is sort of captured in some sense in Mentor. And so I wanted to start by showing Mentor because Mentor, in my mind, is an example. It's a concrete embodiment of the type of software systems we will be building in the future. And there are many takeaways, but the higher order takeaway, I'm actually just going to jump to the slides to explain this one point. The higher order takeaway is this, that the Mentor system is stats based. That's how the ML portion works. And we'll get in a little bit on how that has evolved and kind of the first principles and tenets that we use to build these things. So this is the stuff that you'll see in today's AI landscape: transformers, language models, reinforcement learning, all that fun stuff. Keep in mind, stats-based. So in my understanding of machine learning, all machine learning systems, every single one of them, is stats-based. This is super important to understand. We have a couple episodes on this, and it's my strong conviction that machine learning is, for the most part, advanced statistics. And maybe that doesn't sound super sexy, but that's kind of like the reality of it. And my goal is not to overly complicate or hype things. It's to try to explain it in the simplest terms possible. So if you have a strong understanding of statistics, you likely will be able to pick up machine learning pretty easily. At least that's what happened with me. I don't even have that strong of a background in stats, but I understood programming, I think, a little bit better. And so building machine learning systems was not super hard. But the takeaway here is that on one side of this bifurcated space of machine programming, you have stats-based systems, and they're using machine learning. And to be clear, machine learning systems can be deterministic, stochastic, and anywhere in between in that spectrum. It's important to not confuse or conflate the notion that if a system is machine learned, that it must be stochastic. It doesn't have to be stochastic. It can be deterministic. So the core difference between rules-based systems and the AI systems that we have today that are emerging is the rules-based are essentially governed by observations that we've made through our own understanding and reasoning of algorithms and such. And stats-based are essentially things that the algorithm is learned through data. So if we take one step forward, we see this information. And this is part of the curriculum that I teach. Okay. Now, this is extremely important because if you think for a second, let's just in our heads think that each one of these things is an algorithm. So we're going to build an algorithm that's going to do addition. Well, if it's addition, because we understand addition very well, we would do rules-based. And we can do rules-based for addition based on data that we have from our own understanding and reasoning about addition. We understand the principles of addition, and it's formalized. And so we can create the algorithm as a set of rules. On the other hand, let's say that we want to create an algorithm that's going to tell you if a picture is of a dog or not. Well, this is a lot more nuanced. I don't know that we have the rules. I'm not saying that we couldn't come up with the rules, but I don't know that we have the rules, at least today, to capture in a formal way what a dog is when we just see a photo of it. But we can learn the answer of this, or an approximate probabilistic answer of this, based on data that we train on from data sets. Now, the core point that I'm trying to make here is that the future of software, right? I've actually jumped all the way to the end, or I'm really leaning into the topic so we get right at the heart of it. And then I'll backtrack and explain all of the preamble that gets us to this point. But my view is the future of software is going to be built using building blocks that are both stat-based for algorithm construction and rules-based for algorithm construction. In general, what I think the natural breakdown of this is actually fairly simple. And this is the part where I have to be honest, I'm not entirely sure that I'm right about this. So take this with a grain of salt. I'm still working on figuring this out. We have research discussions. I discuss this with other professors and students, colleagues, you name it. But the higher order breakdown that I have for when it's rules-based or stat-based is mostly rules-based is more of things that we use for hard science. Stats-based are more used for soft science. Now, this is not a perfect breakdown. This is not exactly right. This is why I'm saying I'm not totally sure about this. You shouldn't take this as a strong claim because it's more nuanced than this. I think that there are certain things in soft science that you can apply rules-based types of algorithms to. And on the other hand, I think that there are things in hard science that you can potentially apply stats-based things to, and it works fairly well. And this is in cases when the soft science algorithm or module, it has sort of clear formal properties, then we can probably make it more rules-based. And in the cases where the hard science is a bit more nuanced, or it's like an emerging field where we don't fully understand it, or there are potentially multiple types of hard science solutions, making it more subjective, making it more soft science, then we can use a stats-based solution. Okay, my view then is the future of almost all software is going to be a fusion of using stat-based algorithms and rules-based algorithms. The rules-based is the code that we write today, and it's rules. It's just instructions, and we can look at it. And this is, in many ways, the more straightforward solution, and the solution that we should go to first. And the reason why is that when it's rules-based, we understand the rules very clearly. And when there are bugs in our code, or there's features we need to add, we just go into the code and we update the code, and then it's better. Also, this is based on, in some sense, a very formal understanding of the space. Keep in mind that both of these systems, which is, I think, an interesting observation, maybe I stumbled across last year when I was teaching this at the university, is that both stat-based and rules-based are being formed from data. It's just their sources of data are different. The data from rules-based are basically data that we as a species have learned and we've reasoned about and we've written books about, and we understand these algorithms. And so we know that these things work, like a quicksort algorithm, because people have spent a lot of time reasoning about it, formally verifying it, showing its correctness, and then we can say, yeah, this is good. Use this thing. This thing will sort your stuff in this period of time. That data is essentially data from our human collective brain, our human collective understanding of things. These rules are not coming in from outer space. They're not just like manifesting themselves. They are coming from a huge amount of data and evidence that we have as a species that have hardened to this, and that's why we can rely on them. The stats-based ones, again, are cases where, at least this is the way that I generally use them, is we don't necessarily have the rules, but we do have data that could essentially provide intuitions about what those rules may or may not be. And so while we haven't gone through the process of decades of reasoning about this to generate the concrete rules, we can learn from the data and generate sort of these, what I like to think of as like these geometric spaces that tell you where you are. Sorry, I like to use my hands a lot when I talk. So these geometric spaces are sort of telling you this is in the space of a valid solution for this problem, and these other spaces are potentially not. And then what I anticipate will happen in many cases, maybe not all cases, but I anticipate that once we have a deeper understanding of the stats-based solutions, by observing what it's giving us from the data, and we've refined the data, then we possibly transition the stats-based systems to rules-based. Because ideally, what we probably want more are rules-based, because rules-based, in some sense, gives us a deep understanding of the thing that we're working on, and that understanding allows iterative refinement. So what does this mean? At a high level, what this means is any AI system that we build that can sort of illuminate what the rules of something should be, we should try to then push that AI system into a rules-based algorithm. So then we have it concretely, we can iteratively refine it, debug it, all of that stuff. However, there are likely going to be cases where we cannot do that because it doesn't follow precise rules. And a key area for that I think stats-based are going to remain the primary form of the algorithm is when it's related to things that are not purely mechanical. What I mean by this is living entities. So if you have a system that's trying to interface, a software system is trying to interface with a living entity, so a human or a dog or a dolphin or a bear or something, we don't know what the response will be based on any particular action because different dogs have different behaviors, different humans have different behaviors. Like my Amazon order list is probably different than your Amazon order list. So it's very hard to create sort of a universal set of rules that say, here are the rules that you should apply. The other part where stats-based I think is super useful is when we're doing things that are predictive in nature, that we don't actually have, again, it's not mechanical. We can look at the prior data and then draw intuitions we can speculate, but it's basically us just guessing. And so an example of that would be pick your favorite sports team, and then what do we think the odds are that they're going to win their next game? Well, you could try to build a rules-based system for that, but the truth is that as those sports evolve, and the sports are evolving and they're changing constantly, there's likely going to be things that are emerging that maybe aren't captured in your rules. And there's just a lot of nuance to it. Like, this player plays really well, but not generally against this player. And think about all the different rules that you would have to have, especially as new players come in, old players go out. Like, it would be a lot. But instead, if you had a system that could just churn on the data and continue to update its reasoning with all of that in an automatic way, that might be a better way to do this sort of predictive type of thing. And this is why many of the algorithms that we see in like social media or social related services, like the recommendation system that you see for Amazon, or the recommendation for your newsfeed, is largely AI driven, because it's doing speculation based on things that it's seen historically about what you like, and now it's going to speculate on what you'll like next. And notice too that speculation, if you were to dissect those models, likely the rules that they contain are different for different people. So for example, in my system, it would be probably, if it's related to technology or startups or computer science and AI, make it super high priority. But if it's related to things like sort of movie stars and anything with the Kardashians, generally, especially the latter, generally don't show it to Goju. He's not going to care. And that's not a judgment. Like, by all means, like what you like, but we have different taste. So hopefully this gives you some clarity on what I think the future of software is going to be. And I think that AI is likely to be, so we can think of this as the AI side. And also, the reason why this is called machine programming is it's not just AI. This is the AI. So that's why I don't call it AI for code or ML for code. This is this side. This side also exists, and it's fundamentally important for machine programming, because if it's just all stat-based, then it's just all probabilistic. Like, I don't think that's the future of software development. I think that's pretty boring to me. And I don't think that that's a really good recipe for hard science, I guess is what I'm saying. So now, my conjecture is that the future of almost all software is going to use the two of these. Historically, we've just been here, but now we're going to start doing this. Now, a concrete example of this is Mentor. A large portion of Mentor, all of the visual elements that you see here, this is all traditional software development. This is all rules-based. This is just normal code. But, and by the way, we're looking at Everything Money's repo. We have their permission to show this repository. And I wanted to show you something that's kind of interesting as far as what I think the future of machine programming systems are, and how I think they're very different than what a lot of the vibe coding hype is, and how I think that machine programming systems that are going to be used for sort of production quality software systems will take on a fundamentally different type of approach. And a big part of that is the goal is not to stop coding. The goal is to help software developers do two things, essentially. One, be more productive, and two, produce higher quality code. So, or software, because it could be tests and specifications and all of that stuff that maybe is even data curation that's not directly in the code. Okay, so one more time, the high level goal of machine programming is improving the productivity of the team to build their software system and improving the quality. These two things. So it's faster development and better quality. It has to be both of these, not just one. If it's just faster productivity, you get vibe coding, which is not very interesting to me. If it's just quality, but it's not making us faster, then I don't know that, like, that's cool, but we need to be accelerating the development of software, not impeding it. So along those lines, the way I think about machine programming systems is it's not to replace the coder at all. In fact, I love coding, and I think there's tremendous value in coding, especially for critical thinking. But the way that we interface with the machines may evolve. That I think it's going to be more of you choosing the medium in which you want to interface with the machine, and it should vary. So, for example, some of us are writing TypeScript sometimes. Other times we're writing C, C++. Like we function at different levels based on the different concentrations in the software stack. And the same is true of machine programming systems, is that you may be interfacing at a natural language level to then explain high-level concepts, and then it can do some rapid prototyping. And other times you'll be writing code, and then the machine programming system will then be going in and working on making that code better. And that's what Mentor does. So going back to the bifurcated space, the majority of Mentor is over here in the rules-based system. A large portion of our code is this, but the core engine of Mentor, our ML side, is all in this side. It's all stat-based. What's fundamentally different, though, is our stats-based system is fully deterministic. It's not stochastic, like language models are. And that gives us the reliability that you often need for hard science. And you can also do other things like debug it and iteratively refine it. So to see this concretely, just so you can see that this is not a theory. This is not just I'm giving a theoretical treatment to this space and I'm sort of in an ivory tower saying, well, in my mind, I think you do this. No, we're building real systems that are actually doing this. And Mentor is a concrete embodiment of that. Is that the majority of this code is rules-based, but then if we go to like this latest version of Everything Money and we go into these issues, this is Mentor's ML system that's identified these issues in their source code, and it's essentially not rules-based at all. It's fully based on training this model or many of these models on an enormous corpora of data that then it is able to identify potential issues in the code and then give recommendations on how to potentially solve those. So remember how I was talking about the whole like soft science part? The thing about software code is there's often multiple ways to solve any particular problem. And so Mentor, for example, has these 4 different insights because it's solving this problem like in 4 different ways, because you may like one more than the other. Maybe one's more performance, one's more security, one's more modular, one's more readable, right? Like, and eventually these will have names that kind of mirror that type of thing. But I wanted to show this. And what's really interesting about this is I'm not an expert in JavaScript or TypeScript. Like, I can code in them mostly because I know just general programming language syntax. But when I first saw this, actually, let me back up a little bit and we'll come back to this. When we're working with the Everything Money team, they started using Mentor, I think, right around this date. Is that right? Let me just see the arrow key here. Yeah. So it was on June 5th, I guess. And notice that their score was 467. They had 183 issues. And then they started using Mentor, and their team started going through all of the issues that Mentor had found. And apparently what they saw is that Mentor is pretty good about being right on the issues, which is a key principle that we're trying to promote with Mentor, is that it will be essentially have almost zero false positives. So the false positives, what this means is that it says there is a problem and there isn't a problem. Like, in terms of anomaly detection, it's saying there is an anomaly and there actually isn't an anomaly. That's what a false positive is. And the idea of having no false positives is that we don't want to waste any developer's time with things that are not real issues. However, doing really advanced anomaly detection in the real world, usually you can't have zero false positives and zero false negatives. It's just sort of, it's very hard to do, if not impossible, for highly complex systems. It's easy to do in sort of toy problems, but in the real world, you usually have to make trade-offs. So our trade-off is, while we will try to limit the number of false positives, we will have false negatives. And what false negatives are is that there will be cases that Mentor misses, that there is some sort of anomaly in the code, and Mentor doesn't find it. And we kind of deem this as an acceptable trade-off. What we're going to try to do is, over time, now that we have the false positives to like maybe less than 1%, we're going to try to reduce the false negatives lower and lower without increasing the false positives. We'll see how far we can get. But anyway, what Everything Money did is they started using Mentor, and they had a score of 467, and then they started fixing these issues. So was it, maybe it was this date, maybe it was June 9th. So they had a score of 452, 180, and now you take one step forward in the next day and no change. Okay, maybe we'll start here. Then, sorry, I'm getting ahead of myself. Then in the same day, they run inference again, and they fixed 19 of these anomalies. And so their score goes up by 16 points. Then the next day, they fix 28 of the issues. Their score goes up by 27 points. They continue to do this. They fix another 20. Their score goes up. They fix another 7. Score goes up. Another 18. Score keeps going up, and so on and so forth. Now they get into the good range, right? And where they are today is here. Or I guess that was yesterday. So they went from a score, or their current Mentor score, of like 440, and over the course of like 3 weeks, they were able to improve their software's quality, at least according to Mentor, by 250 points, which in my mind is crazy. This is one of the fastest course corrections in quality that we've seen from any customer that we've worked with. It's like mind-boggling. That so now they're at 43 open issues, and you can see in this graph, right? Like, so this is where I think this is where they started. Sorry, no, it's here. This is where they started using. Wait, hold on. Maybe it was. What day is this? Okay, there's still some UI clicking bugs. Okay, yeah. So they did start here, and they had 180 issues and a score of 440. And then you can see that these are the issues. They're bringing it down, bringing it down. It's almost to zero, and you can see that their score is going up, 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 up. And so 180 issues, and now where they are today, 43 issues. So they fixed almost 140. And what's really interesting when you use AI systems, I think, the right way, or maybe in a way that is just more responsible, other than just throwing AI at any problem, it can help you do things that you might not otherwise be able to do. So, for example, again, I'm not a JavaScript expert or TypeScript expert, so I wouldn't even know what rules to write for JavaScript to make JavaScript better. But I do have a pretty advanced understanding of machine learning, and I understand how the machine learning systems can be designed and trained on highly reliable, trustworthy code in various different languages. That's part of the novelty of the Mentor system, is the way it performs semi-trust training, which, if you're not familiar with, I encourage you to check out some of the slides from my class on my website. But so I was curious if the issues that Mentor has been finding if they're valid. And keep in mind, we have Everything Money's permission to show you this code. Part of the reason why I think is that this is all TypeScript, so it's already out there. You just right click and view source, right? So what I did is I was just curious, okay, so what are some of these issues? And I went in and I saw this thing here. Now, again, not an expert in JavaScript. I know what an if is, so I get that. I recently learned what this triple equals is, and what I think it is, if I'm recalling correctly, is double equals is the normal equality, like these values are the same. Triple equal is that the values are the same and the type is the same. So you could have like this be an integer and this be a float, and double equals would say if they're both the number 7 that they're equal, but triple equals would say they're false. That's false because they're not the same type. On the other hand, if they're both ints and they both have the value 7, then triple equals would basically tell you that it's true. At least that's my understanding. Again, not an expert in JavaScript, TypeScript. Feel free to tell me I'm wrong in the comments. Now, this character here, I didn't know what this was. And what I wanted to do is I wanted to pick one of the easiest, simplest anomalies and see if Mentor is like right about this. Keep in mind, as sort of the chief scientist behind the design of this, a lot of this is from my sort of deep thought on programming languages, grammars, intermediate representations, and machine learning, right? It goes back to those 4 domains that we've talked about in the past. Right here is to build machine programming systems, you generally need machine learning, software engineering, system architecture, and programming languages understanding. And yeah. And so while I don't have a mastery over JavaScript and TypeScript, I do understand this pretty well. I understand this pretty well. I understand this pretty well. And so the idea is, if I could capture the high-level concepts that I think are relevant for programming languages, and then those can be kind of like distilled out, then if you had enough high-quality data, you could essentially learn what the rules are based on that corpora of data. So the idea I had here is, let's look at this. This looks super simple. This can't possibly like actually be an anomaly, right? Like it's just again, I don't know what this plus operator is, but otherwise this doesn't like look like it's an issue to me. So I went in and I think it's this first one. Yeah. I went in and I read about this, and this, and again, this is all Mentor teaching me. And part of the goal of Mentor is not just to solve the problem, it's to teach. Because the idea with Mentor is we're not trying to replace programmers. We're trying to educate them, like including me. I don't know about JavaScript and TypeScript. I want to learn, right? And just because you don't have mastery over programming language, for those of you that aren't experts in C++, it doesn't mean that you're dumb. It just means that you just don't have the knowledge yet. So Mentor can help you build up all the knowledge while you're actually fixing the code. So I look at this with Mentor, and it tells me, this plus operator converts both values to numbers before comparing them. And then I was like, oh, okay. So the unary operator is used to convert this to a number. If this is a string that represents a numeral, it will be converted to a number. And then it dawned on me, oh, what if it's a string that cannot be converted to a number? Then it's a nan, right? It's not a number. And not a number can't be compared to a number. It's not a number. It's like division by zero. There's no, it's an exception, essentially. There is no integer or numerical representation for this thing. It's not a valid op. So even trying to do the comparison operator is like, this just doesn't make sense. So when I saw that, I was like, oh, right. Okay, so maybe Mentor is not crazy here, that what you probably want to do is check to see if this is a nan, check to see if this is a nan, and if they are, you say, nope, it's just, you can't even do this. It's false already, or it's something else. It's like, it's more than just false, because they can't be converted to the numbers that you would compare against. It's an invalid type error, essentially, if either of these are nan, or both of them are. So with that, then I realized, oh, this is probably like what it's complaining about. And then I see this, and yes, like, so Mentor's like basically talking about this. This is actually a crash bug. This is potentially a crash bug. And so I'm looking at least this is my understanding, right? Again, not an expert in JavaScript, so I could be wrong. If you are, please let us know in the comments. So then I look at what Mentor rewrites this as, and basically it does this check now, is that it's going to try to convert both of these things to numbers. And if it is a nan, it basically says this is just null. Otherwise, it gives a number. And then it changed the if. So if either of these are null, then it just exits out. I think that you could probably do a little bit better. It may want to return some error, but I guess the end user can refine this. This is also, again, going back to that point that, like I was saying, Mentor doesn't always get the solution exactly right. And so in this case, I think Mentor's solution, this would work, I think. You could basically copy paste this in, and I think this would actually solve the problem. The issue that I have with it is I think that it could be made even better. And that is, if either of these are null, then it probably wants to do something else, like potentially, I mean, it depends on what the logic here is. Like, I see this try block, so it means it's probably expecting some sort of exceptions from this code. So it might want to throw an invalid type comparison exception. We'd have to look at this deeply to see what we want to do. But anyway, I would slightly massage this so it could do two different things. That if they're not numbers, it could do one thing. And then if they are numbers but they're not equal, then it can do something else. Or I guess in this case, if they are equal, it would return null. And if they aren't, then it would do something else. So there's probably like at least 3 different types of things that can happen. Now, the takeaway for this is not, oh, Mentor is amazing. I mean, sure, I like Mentor a lot. It's the point that I was trying to make about the future of software is that when you have stats-based systems and you have data on problems that you are like potentially not an expert in, like I was saying before, you don't necessarily have the rules because you haven't figured those things out. Like you don't know exactly what a dog is, but you have a whole bunch of pictures of dogs. You can't quite figure this out. Or potentially this is an enormously hard problem and writing the rules could take you decades. That maybe you throw an ML system at it, and then now it essentially gives you this probabilistic system that helps you solve this problem. You have to keep in mind, though, that when you start moving into the space with stats, because it's probabilistic and all stats-based systems are probabilistic, that's in the word, right? Statistics. It's about stats. It's about the actual distribution of data and what the probability is of things to happen within that distribution. That's basically the foundations of statistics. So it is probabilistic at its core, but as long as you're okay with it being probabilistic, then it can be super helpful. Like, for example, the recommendations on items that you're going to buy on Amazon, they are probabilistic. There's no guarantee that you're going to buy these items. You can base it off of things that you've bought historically, but what about stuff that you are going to be buying for the future? Like, for example, let's say that you buy a flashlight, and so it knows you're buying a flashlight. Well, the next purchase could be batteries for the flashlight. Now, you could probably create a rule for that, but imagine like the potential innumerable cases where there's so many secondary or tertiary items that you might want to buy, that writing the rules for all of that, especially as the rules themselves evolve, it might just be better to have that be a probabilistic system. Like, for example, if you buy a camera, what's the next thing? Extra power brick, various zoom things, add-ons for microphones, who knows? There's like a slew of things. And then also those products are going to evolve. And so you want a system that's maybe going to offer like the latest and greatest or the highest reviews, or maybe this person prefers things that are really inexpensive to high quality, right? So you can see how this can be much more customized over here, and it can do it in a little bit more of a nuanced way. It's my belief, when you sort of consider this all together, that the future of these software systems is going to be very much a fusion of these two things. But what I think a lot of people are doing right now is they're going a little overboard with it. They're trying to force the AI piece in places where it doesn't necessarily make sense. Like kind of what is happening with the vibe coding thing. Again, remember what we were talking about with the rules and hard science, is that the vibe coding thing is largely based on this probabilistic thing, and that probabilistic thing is also stochastic. While Mentor is also probabilistic, it's deterministic. And then that moves it more into the rules-based space, is that it's still trained like a stats thing, but then it can be debugged and iterated on almost as if it's rules. Now, what I think the future is going to hold is you don't necessarily have to build your own ML system from scratch, right? We're already just using these models. But I think that we should be very careful in the way that we think about how we should apply the stats-based side. Like I saw some, I'm not going to actually mention the software that I saw this in, but I think Taylor and I were looking at this, and there was someone using AI in a really not super great way, and it was almost like a fundamental architectural problem with the software system, the way that they're designing it, that if they start to use this AI, yeah, let me see if there's a way I can explain this without explaining what the software is. Uh, the the short of it was they were using they yeah, I don't think I can do it. I think if I try to explain it, it's gonna give too much detail. So I'm not gonna do that. But basically, it was using an AI in a way that you should have probably been doing the rules. Like you should have. There were rules that you could clearly follow, and those rules are sort of public domain. It's not confusing at all. But instead of doing that, I think it was sort of like the shiny new toy. Like, oh, let's use the AI to do this instead. And the danger there is that this, when you have the answer that's super clear, like for example, if you know that you're playing baseball and 3 strikes is an out, you should just have a rules-based system that's counting the strikes. So they swing once, that's a strike, twice, strike, third time, they're out. You could do it in a stats-based way, but why would you do that? We know what the rules are, and the rules are actually not that hard. So this is what I'm talking about is as we move forward with software, I strongly believe it's going to be a fusion of these two things. I strongly believe that the hard science stuff, like strikes for an out, is actually hard science because it's deterministic. It has some sort of objective reality to it that everyone can agree on, as long as we all agree that the person swung the bat. That part is a little subjective. That's actually maybe a really interesting example of how you can have something that is in the hard science space, but it has some subjectivity to it. So maybe the umpire ruling would be on whether or not it's a swing. Maybe that would be the stats base. But once it decides it's a swing, the rules based system kicks in. You don't count the strikes in a stats based way. Now, you could. The problem with this is that when you get to 3, the stats-based system might say, yeah, it's not an out. Let's have this batter have 4 strikes. And that's going to break the rules of baseball. And that's an example of sort of a misuse, in my mind, of stats-based stuff. And it's also an example of why I think the vibe coding era is sort of doomed in terms of production quality software, because production quality software, for example, just shouldn't crash, right? And when we look at this code and we see that Mentor is saying, oh, this is an issue and it could potentially crash, I think we can probably all agree that, oh yeah, crash bad. No crash. Let's make the code so it's impossible to crash. Not a 99% of the time it's not going to crash here, but in that 1% it might. No, that's not sufficient. We already have enough of the 0.001 cases that it could crash, like the power could go out or the data files it's reading could be corrupted. You know, there's things outside of our control that can go wrong. The stuff that's inside of our control, we should try to get as deterministically correct as we can using the traditional systems, and using the new space of the stats-based system only in the cases when the historical old way won't suffice. Okay. At this point, I actually did not talk about the stuff that I want to talk about in the order. I did it sort of the opposite way. We dove right into the software, and then we talked about the bifurcated space, and I didn't talk about the old way to do software and the 3 pillars. So I'm going to attempt to do this really fast, mostly just to wrap this up, but I'll probably do a follow-up video where we can talk about this in more detail, because giving it sort of a really rushed treatment is probably not going to be as compelling as I think it probably needs to be. But in essence, the way that we've done programming in the past is, for those of you that are building systems from scratch, or you've been on large development teams, the short of it is we have an idea for some software in our head, and that's sort of our intention. And then we try to manifest that intention. We try to have an embodiment of that, and then it ends up looking sort of something like this, is that we have our intention that gets embodied generally by these 2 spaces. There's the algorithms and data structures, which is sort of the traditional definition of software. But then there's also the system implementation part. And this part is often maybe not included in more of the academic discussion, or at least from what I've seen, but I think it should be. And the reason for this is that almost all software systems have to deal with actual practical systems. And what I mean by this is, like, if you're working in JavaScript and TypeScript, there are likely going to be cases where you need to say, okay, wait, what browser is this? Because this browser is going to have this type of behavior. This browser can have this type of behavior. Same thing with operating systems. Same thing with CPU versus GPU. Like, there's system-related details that are going to impact the way you design your software. So it's not just, you could try to capture this in a general sense, but oftentimes you're going to have specialized behavior based on this. Now, you may notice that the picture that I have here is we've got a large portion of the programmer intention covered by these clouds, but not all of it. There's programmer intention of what we want to build with the software that's not covered by this. This is not an accident. This is very much how Mentor is today, is that what Mentor is today is a very awesome piece of software that does a lot of really cool things, but this is not at all fulfilling the intention that I have for what Mentor can and should be in the future. It's only some small portion of that. It's probably maybe 10% of the intention that I have in my mind. And so that's why there are these gaps here, is that we don't necessarily get the software that we have in our mind. And on top of that, when we're just doing code just as humans, there's so many things that we have to juggle. One, coding is slow and error prone. Like, humans get tired. I get tired. I make mistakes. You've seen me code and make mistakes. And I'm a supposed expert. And if I'm been doing this for 30 years and I'm still making mistakes, what about people that are new to it? Also, you have to hold multiple dimensionalities in your head. Correctness, security, performance. This can be really difficult. On top of that, code is evolving in this way that makes it a multifaceted challenge. You can have, for example, code that works perfectly and everything's great, and then the ecosystem in which you're using it changes underneath you and no longer works. This happens all the time, especially as operating systems evolve. And then they decide, well, it's not going to be backward compatible. Your stuff doesn't work now. Welcome to the Apple M series chip, right? Whoa. Now we have more work to do. So there's a lot to do here. And the idea with machine programming is we can use the machines to help us with some of this stuff, that we don't have to do all of this on our own. And a program, as we point out over here, it consists of the intention, code to express or misexpress that intention, specializations for all the stuff. And it's even harder because the automation systems have blurred lines on what is what. And what I mean by that is it doesn't have a clear understanding of what is the intention versus what is the implementation. And that's not super great. So in come the three pillars. You have intention, invention, adaptation, right? And I'm going to just zoom past this. If you haven't seen this before, I think there's a couple VODs, and maybe I'll talk about this in more detail in a follow-up. But one of the biggest things is this idea of separation of concerns, that the intentionality should largely be separate from the invention and adaptation of those software systems. And a big reason why this is super important is that once you move into the invention or adaptation space, you start to build a specific embodiment of that intention. As we just saw with Mentor, there are likely numerous embodiments of an intention. But if you don't have separation of concerns here, what can happen is you can have implementations that then get conflated as intention, and then the MP system doesn't know where the lines end for what is the intention of the software system versus the implementation. So that linked list that you used for this thing, it thinks is part of the intention, and now it doesn't try to optimize that away into a more efficient container like a binary tree or a red-black tree or something like that. And so you're stuck with this linked list, and suddenly your performance is abysmal because you accidentally didn't have separation of concerns here. That's just one example. There's numerous. But the big thing is this idea of allowing the machine a wider range of possible solutions when you separate the intention from the implementation. And both of these things are related to the implementation. The invention part is sort of the core algorithms and data structures that you need. I can kind of think of these as like high level, like pseudocode maybe, or Python code or something at a high level that's sort of a prototypical whatever. And then the adaptation is more of a, now let's make this run efficiently. The adaptation can also be about adapting the existing software system to make it better. So Mentor is an example of both an inventive and an adaptive system. So it's adaptive in the sense that it's going to take existing source code and it's going to try to make it better. It's going to adapt it, but it's inventive in the sense that it's not just flagging the things that should be resolved. It's inventing solutions that don't currently exist to then resolve these issues. So it's actually a duality. Yeah, and you may see some intentionality work in Mentor in the future. Okay, that's basically the higher order bit that I wanted to share on going over this. I may go over this in the future just to add a little bit more color, but my hope is that now you have kind of an understanding of, like, this is sort of the old way that we have done code. And it's worked, but it is a bit of a mess, I think, especially when the system implementation stuff gets blurred into here and we don't really know what the intention is. This happens all the time. And, specifications of software are usually disjoint from implementations. Implementations are sort of just like our best effort on trying to get some sort of specification right. And the specifications for software systems oftentimes are in things like natural language. They're prose, which can introduce ambiguity, right? So it's complicated. And it's going to remain complicated, even with machine programming systems. But hopefully with AI systems, we can have back and forth to really tease out what the intentionality is. And the intentionality, just keep in mind, the intentionality doesn't have to just be natural language. Intentionality can be expressed abstractly or quasi-abstractly in code as a high-level idea that then can be you can lift out the semantics of what the idea is expressing and then rewrite it in a more inventive way. This, again, it needs a lot more discussion and treatment to fully understand. But for those of you that have been studying machine programming for a while, you may already glean what I'm saying. A concrete example of this, if you're curious to know more, is to look at Professor Alvin Chung's research in verified lifting and MetaLift, which does something very similar. It takes a concrete embodiment of a system, which is its actual code. It then lifts out the semantics, which is a higher order representation. It does this automatically in like a formally constrained, reduced grammar PL that just captures the semantics. It elides away all the PL specific code. So if this was Java before, when it lifts it into the higher semantics, it's not Java anymore. Then when it understands that intention, it then lowers into another language like C++. And the purpose of the verified lifting is oftentimes performance, but you can do it for security, for readability, for transpilation from legacy languages to newer languages. So this is the idea that I'm trying to get across, is that you don't have to have intention just expressed in natural language. You can express intention actually in code and then say, now lift out the semantics and then do other stuff. And in fact, a part of what Mentor does that makes it sort of, I think, magical compared to many of the vibe coding systems is that we do this. That's part of our secret, is we lift out the semantic meaning of code into a higher order abstraction on things that we've invented that capture the essence of what the code represents. It's discussed sort of briefly in the MIT article that Will Heaven published, I think, earlier this year. But that's just one of several intermediate representations. But so the thing I'm trying to get across is that when you think about intention, it doesn't have to be just natural language, like what the vibe coders are doing. You can express intention actually in code. And I strongly recommend this because when you express it in code, you elide away ambiguity. And it becomes more structured. And the likelihood of then it being able to lift out the semantics and then rewrite this, reinvent it, and adapt it in a precise, perfectly captured way from the original intention, which was code, is probably much closer to 100% than if you use natural language. Because natural language is ambiguous, it's unstructured, and it's not guaranteed to actually capture the intention. It can speculate on it. So this is one of the things that I think, like, it's good for people that are not coders because they can just write natural language and then get a piece of software. I think that's totally cool. I actually love that. Okay, I love that we're expanding the horizons and people that can like generate software. That's why the intention pillar here says nothing about the medium, the vehicle in which we'll express the intention. If you look at the original 3 pillars paper, I think it talks about things like visual diagrams, natural language, programming language, code. It's just whatever you want, whatever is best for you. For me personally, it's actual software code. I'd probably use something like Python to capture the semantics. Maybe I actually haven't looked at Mojo, but Chris Latner is a very smart guy, and I think. Let me rephrase that. Chris Latner is a very accomplished individual in the space of programming languages and intermediate representations. I'm fixing myself from the last. I'm not praising someone for their intelligence. I got a bad Goju. Bad. Praise them for their accomplishments. So Dr. Latner has had a ton of accomplishments, and I will look at Mojo at some. In fact, if anyone that's watching this has played around with Mojo and has good things that we can look at for Mojo, I would love to hear about that in the comments. So with that, I think that we're good for now. If you take one thing away from this episode, it would be that while this class that I teach is explaining how to build machine programming systems, it's also my view that this is how essentially the future of software systems are going to be built. And in fact, we're seeing it already today. Mentor is one example of that, but many of the software systems that you see that I think are actually maybe using this in a way that makes a lot of sense are doing the divide the way that I just discussed. Like one example of this is Opus Clips. Opus Clips is largely rules based. So they have a whole bunch of video processing, and it's a website, and it's just a lot of actual engineering. But the stats-based side is they have what I believe is a natural language processing element and a video processing element, and then it learns where the sort of the highest virality score for the clips will be, and then it does those in an automated fashion, and it's entirely based off of a learned stats-based model. I think that's an excellent way of using machine programming. That is a machine programming system, and it's using one side that is rules, large, like maybe 90%, if I had to speculate, is maybe rules based, and maybe 10% is stats based. But the 10% stats based is something that without that, you might not be able to build a system like this. Like, how would you create the rules to then process the natural language and understand, oh, this is the beginning of a new section, and oh, here's the end of the section, oh, and it fits within these constraints, and we can elide away dead space and filler words and things of that nature. These are nuanced and more, I think, subjective. Okay, cool. Thanks, everybody. I hope we all learned something, and please share in the comments if you have more to add. I am particularly interested in that Mojo question. In fact, with Merly, I think I meant to reach out to Modular AI. I'm glad we mentioned this because maybe I'll do that after this recording. Cool. Thanks, everybody.